Hello everyone, I'm Vikram Madduri here. I'm a software architect and welcome to Softech. This would be our part 6 of the first chapter in machine learning concept. We are discussing the introduction part of machine learning where we are discussing about various basic topics that we must know before we learn the machine learning concept. Now, in the previous sessions, we discussed about a taste of machine learning applications, data, and the problems that we normally face in our activities in the day-to-day life and in the business as well. The probability theory, and we have discussed about the random variables, distribution, mean and variance, marginalization, independence, conditioning, and Bayes rule. So, regarding the marginalization, independence, conditioning, and Bayes rule, I'm going to revisit this topic and explain you more in detail in the coming sessions. Right now, in this session, we are going to discuss about the basic algorithms, in which we are going to first discuss the naive Bayes rule, and then we have nearest neighbor estimators concept, and then we have the a simple classifier, perceptron, and k-means. So we'll see. Basically, we'll first focus on the naive Bayes rule right now, and let's see the other things later. Now, basic algorithms. So we conclude our introduction part to the machine learning by discussing four simple algorithms, namely the naive Bayes theory. We have nearest neighbors, the mean classifier, and the perceptron, which can be classified used to solve a binary classification problem such as that described in the figure 1.5, which we're going to discuss now. We'll also introduce the k-means algorithm, which can be employed when labeled data is not available. All these algorithms are readily usable and easily implemented from the scratch in their most basic forms. For the sake of concreteness, assume that we are interested in spam filtering. So this we are taking a scenario wherein would like to filter the spam emails and would like to apply the machine learning concepts there. That is, we are given a set of emails, that is m emails xi, so denoted by x is equals to x1 to xm number of emails. Now let's consider a example of a mail that we have received from a particular email id to our id, and we have a particular subject there, and in this we have a couple of things that have been mentioned in the text, in the subject, and in the content of the email. Now here, if you see, there is a line called the quick brown fox jumped over the lazy dog. There is another statement called the dog hunts a fox. So these are the two things that we have here, and we would rearrange this as the quick brown fox jumped over the lazy dog. And after that, we have in x2, we have the is already been there, dog is already there, hunts is not there in any of these words which are being mentioned in the first sentence. So we'll write down hunts, and there is a. The A is something which is not in the first sentence, and that we are going to write it here. Now here, x1 represents the first sentence and x2 represents the second sentence, and the occurrence of B in the first sentence is twice, and all the occurrences of other words is one time. Hans and A have been, we come across those things in the first sentence only, not even once, so it's 0 0. Then we have this x2 where we have a couple of things as one time and others as not even once at all. So vector space representation of strings. This is a vector space representation of strings. Now associated labels yi denoted by y is equals to y1 to ym. Here the labels satisfy yi belongs to spam or ham. So there are two things here. Either it can be spam or ham. The key assumption we make here is that the pairs xi, yi are drawn jointly from some distribution p of xy, which represents the email generating process for a user. Moreover, we assume that there is sufficiently strong dependence between X and Y, which represents the email generating process for a user. Moreover, we assume that there is sufficiently strong dependence between X and Y that we will be able to estimate Y given X and a set of labeled instances of XY. So we need to understand this. This is something which we come across in a very regular basis in our math classes. So if a couple of instances of xy have been given, and if at any point of time if you give the x value, we can include the value of y. In some cases precisely, in some cases approximately. Before we do so, we need to address the fact that emails such as in figure 1.14, this is the email that we have here, are text, whereas the three algorithms we present will require data to be presented in a vectorial fashion. So one way of converting text into a vector is by using the so-called bag of words representation. And in its simplest version, it works as follows. Assume we have a list of all possible words occurring in X, that is a dictionary. Then we are able to assign a unique number with each of those words. And now we may simply count for each document xi the number of times a given word j is occurring, then used as the value of jth coordinator. And in the figure 1.15, we understand the concept of we understand the same representation. So once we have the later, it is easy to compute distances, similarities, and other statistics directly from the vectorial representation. So this is a vector space representation of the strings that we came across in the email. So now, what exactly is naive Bayes rule? This is what we're going to discuss now. Let me rewind what we have discussed. We are just trying to understand a particular concept of basic algorithms. And we have a task in our hand that we need to find out what are the spam emails that we are getting, and we need to identify them and check them. So for that, we are following this particular method of vector space representation of strings. Now, coming to the naive Bayes rule. So, in the example of the AIDS test we have used in the earlier sessions, the outcome of the test to infer whether the patient is diseased. In the context of spam filtering, the actual text of the email X corresponds to the test, and the label Y is equivalent to the diagnosis. So, recall Bayes rule. We could use the latter to infer P y of x is equals to P x of y, P of y by P of x. So we may have a good estimate of P of y, that is the probability of receiving a spam or a ham mail, denoted by m ham and m spam, the number of ham and spam emails in X. And in this case, we can estimate that P ham is approximately equal to m ham by m, and P spam is approximately equal to m spam by m. So the key problem, however, is that we do not know P of xy or P of x. So we may dispose of the requirement of knowing P of x by settling for a likelihood ratio. So for the likelihood ratio, the equation would be L of x equal to P of spam by x by P of ham by x is equal to P of x by spam and P spam by P of x by ham, P ham. Now, whenever L of x exceeds a given threshold C, we decide that x is a spam and consequently reject the email. So if C is large, then our algorithm is conservative and classifies an email as spam only if P of spam by x is greater than P of ham by x. On the other hand, if C is small, then the algorithm aggressively classifies emails as spam. So the key obstacle is that we have no access to P of xy. This is where we make our key approximation. So if we recall 1.3, in order to model the distribution of the test outcomes T1 and T2, we made the assumption that they are conditionally independent of each other given the diagnosis. So analogously, we may now treat the occurrence of each word in a document as a separate test and combine the outcomes in a naive fashion by assuming that P of xy is equal to pi j is equals to 1 P of w bar j by y. So then a couple of words in x. Now where w bar j denotes the jth word in the document x. This amounts to the assumption that the probability of occurrence of a word in a document is independent of all other words given the category of the document. Even though this assumption does not hold in general, for instance, the word York is much more likely to occur after the word new. It suffices for our purposes. So this assumption reduces the difficulty of knowing P of xy to that of estimating the probabilities of occurrence of individual words W. So estimates for this naive base model is what we are discussing. So here we have y, word 1, word 2, word 3, word uh, to the n number of times. So here, naive-based model, the occurrence of individual words in independent of each other, given the category of the text. For instance, the word Viagra is fairly frequent in y is equals to spam, but is considerably less frequent in y is equals to ham, except when considering the mailbox of a Pfizer sales representative. So P of WY can be obtained, for instance, by simply counting the frequency occurrence of the word within a document of a class. That is, we estimate that P of W by spam is approximately equal to sigma m to I is equals to 1 sigma number of words in xi and j is equals to 1. So we have I is equals to 1 to m and j is equals to 1 to number of words in xi into yi is equals to spam and w bar ji is equals to w by e and by sigma I is equals to 1 to m, then into sigma j is equals to 1 to number of words in xi into yi is equals to spam. Now here yi is equals to spam and w I to j is equals to w equals 1 if and only if xi is labeled as spam and w occurs as the jth word in xi. The denominator is simply the total number of words in spam documents. Similarly, one can compute P of w by ham. In principle, we could perform the above summation whenever we see a new document X. So this would be terribly inefficient since each such computation requires a full pass through X and Y. Instead, we can perform a single pass through X and Y and store the result statistics as a good estimate of conditional probabilities. So I'm going to take it forward. I'm going to explain you more further about this particular estimate that we are going to make and the naive based model. I'm going to continue from here in the next session, wherein I'm going to explain you more in detail about the naive based rule and how do we conclude that a mail is probably a spam. The more we calculate and the more precisely we do the calculation, the more perfectly we can find out the spam details, spam mails. If you would like to encourage us to do more such videos, do like our session and share it with your friends so that it will help them as well. And do not forget to subscribe to our channel. In case you need any kind of machine learning training, you can contact us.